Hi, my name is Vahan Davudyan. I'm a physics experimentalist for 30 years, and today our topic is going to be renewable energy and global warming. This is so important in our life because we deal with energy every moment in our life, and unfortunately, the consequences of using fossil fuels and some other things and causing global warming. So I had to add global warming. This is going to be so comprehensive. You're going to love this, you know, video, and I'm hoping that I will cover everything to the best of my knowledge, to the best of my ability. Because conversion of energies are so important in our life, no matter what. Always we use that, to generate electricity. But I had to bring in the laws of thermodynamics, which is the most fundamental forces in the nature, and especially first and second laws of thermodynamics. And then I will give you some example. And in fact, today, beside these posters, I have a few presentation for the experiments. I show you exactly what I mean by the conversion of energies, which is so easy to understand and so easy to visualize. Well, I have to start with this poster first, and then I will show you those experiments. So, Renewable Energy and Global Warming by Vahan Davudyan, physics experimentalist, and this is my email, vahandavudyan at aol.com. Like I said, we do deal with energy every moment in our life, and then I had to make a pie chart like this, and then you can see this is like 360 degrees, but you can see the coal is almost 25.5% of the energy we use, and the oil is the most. Imagine we are using 32% oil, and then the gas we're using 21%, and then renewable energy and nuclear energy is only 21.5%, which is this green part. Well, of course, out of this 21.5%, I had to break it down. So you can see here, hydroelectric is the best, which is 26.5%, but overall is 5.7% of the whole. And then biomass and the wood waste crops is almost 41%, which is 8.8% of the whole. And then we have also like nuclear, which is 23%, which is 4.9% of the whole. But overall, this is the breakdown for the energy, and then you can see this also, that's, this renewable energy here, breaks down to some other things. One of them is geothermal, which I will explain it, which is 19.2, which is even less than 1%, and then biofuels is 13%, which is also less than 1%, and then the other one is the solar, which is, we use this a lot, and then there's another one which is a little bit different. Maybe you never heard this. It's called ocean power, which is called the tidal. We have to see what do we mean by the renewable energy. Every time you go to gas station, you fill out your tank, and then you travel from Los Angeles to New York City. You have to stop by so many places and get gas. It depends on how big your gas tank is. But overall, that gas is going in. That emission goes in atmosphere. So in other words, that gas is not renewable, and no matter what, always we're polluting the environment and then the atmosphere and everything. So this is the explanation for this worldwide energy usage. Renewable energy is almost 21.5%, and then it's the hydroelectric and nuclear, which in fact it happens that the hydroelectric is the best, biomass, and then I told you before that is the waste, is the wood and the waste crop, and then that contributes the most. But what do we mean by renewable? It is replenishing, naturally, or in other words, we don't have to get gas. Like I said a few minutes ago, you don't have to get gas. You don't have to replenish, like sunlight is always there, and then we don't have to do anything. And another one is a radioactive decay, which will explain uh, later. But overall, this is an important fact. So renewable energy is generated from the sources that are naturally replenished. Sources like wind, sun, rain, and also geothermal heat. So let me take this off so I can show you what I mean by the laws of thermodynamics. That is so important. I have to put this off. This is a small pendulum, and I realize if I show you this, you will exactly visualize what do we mean by the conversions of energies. And this is the best thing I could think of. Well, of course I have more. And then imagine I had this like October 9 a year ago. That was great success, almost like 300, 400 people watched it. And then that was the time I came back from France. And then I was in the same site, Mr. Foucault did in 1851. And that was best moment in my life because, I made a physicist and he was fluent in English. And I was there almost half a day. Most people walk in and walk out in Pentium and they see that, Mr. Hoku did in 1851, but I had to wait there like 4 hours. I did all the dimensions and then I discussed with that physicist, and he was a great person because he was on site. Then it looks like there was another person, showing people what things are, but he had plenty of time, so we did this. But that was great success when I did this on 2023, and you can watch that. So it's called Earth rotation and the focus pendulum. And this is the easy way to understand. Imagine this is the pendulum and this is the bob and this is the rod, or the string, or whatever you can call it. And imagine this 250 is always pointing to the center of the earth. And it doesn't matter how I change the orientation of this pendulum, look. It doesn't matter. It's always pointing to the center of the earth. See? It doesn't matter how do I do that. It's always like that. And if you remember, according to Sir Isaac Newton's universal laws of gravity, it is pointing to the center of the earth. And it doesn't matter how I do it, always is coming back to the same place. But there is something amazing happened here. This is the only way I can show you how easy it is. You can see the conversion of energies. First of all, I like to talk about the laws of thermodynamics, and these are so fundamental forces in nature, and then our entire universe is governed by laws of thermodynamics, and especially second law. So first law states that in simple language, you cannot create energy nor destroy it. Energy is converted. And the second law is more important. It says, every time you have something in motion, we have entropy. Entropy means that, disorder is a Latin word. So every time you have something moving, you have like friction, you have some other things. So it's slowing down your motion. And then I will explain later. And imagine this is called a state of equilibrium. So in other words, there is no force acting on this bob or acting. But when I displace this, it means that I'm giving more force. So the best way to say in science, I'm investing energy in this. So I'm pushing this because I'm and then I'm displacing from the space of equilibrium. And then imagine when I let go, what happened? Gravitational potential energy, see, is going back to where it came from. But something amazing happened here. So now here we have no energy at all. But here, as I raise this or I displace this from this So what happened? I'm raising the gravitational potential energy. See, it's not now I'm half. When I come over here, gravitational potential energy is exactly like would say 100%. When I let go, this is called restoring force. The restoring force means that the gravity is pulling this bob, and no matter what, because it has a pivot over here, and then I had to use real good ball bearing over here, so it has to go here. But something amazing happened here. When I let this go, see what happened. When it comes to this position, gravitational potential energy is almost zero, but at the same time, this, you know, 90 degree, it gained a lot of kinetic energy. So uh, that's why it's propelling this forward. See? So gravitational potential energy is here zero, but kinetic energy is the most. So that's why it's propelling this way. So let me do it again. You can see, so it's exactly conversion of gravitational potential energy to kinetic energy and back and forth or vice versa. But something amazing happened here. And the second laws of thermodynamics always comes in equation, because there is no way that you can avoid that. So once I let this go, this is swinging back and forth, back and forth. But sometimes you can't see that because the period is back and forth is called one period. Well, it's not 180 degrees, we'll say maybe 120 degrees. So every time it goes back and forth is exactly 1 second. So it's half a second for this part and half a second for this part. But see what happened here. It says doing some work. What do we mean by doing some work? This bob or pendulum is moving air, because see, we are not doing it in this vacuum, it doesn't matter. So this is pushing air. So every time the swing, and then you can see, let me see if you can see I put like graduations over here, you can see. So every time it's becoming smaller and smaller, and finally the friction on my pivot and friction, air friction, will stop it. And it doesn't matter if I take this to the moon, which is no air, still is going to stop after a while because we have a friction over here. If I take this to Mars, it's going to be less because the restoring force in Mars is 1/3 of it, but on moon is 6 times less. But now on Earth is 9.82, and this, S2 or a square. So what happened? It doesn't matter where I take this, pendulum works always the same. And it's independent of the mass. If I change this to 400 grams, still the period is going to be the same. Back and forth is going to be the same. And I had to do this chart so you can see that is so important that you know this chart. And I had to put this formula, which happened to be extremely important formula in science. It's called kinetic energy, and you can see this is a formula. It's half of mass velocity square. That is so important. Imagine if you increase the mass by 2, the kinetic energy will be 2. But if you increase the velocity by 2, is multiplied by itself is 4. So that's why the kinetic energy is so good. Some asteroids coming toward the Earth, and they gain so much millions or billions of joules of energy. That's why the devastation is beyond your imagination how bad it is. So this is the formula. So let me put this down, and then I can start another one, which is also the conversion of energies. So you can see. This is so heavy, I have to be careful not to drop it because this key box is so heavy anyway. Okay, you can see I have the electric motor here, which is 12 volt, and this gearbox I made, well, of course, this is from the motorcycle, and then the ratio is 11 to 1, so every time I rotate this hand torque it, so I can go maximum like 1440 RPM, but this electric motor needs exactly 3000 RPM, so that's why I'm only generating 6 volt. So it's easy to understand what do we mean by the conversion of energies. If I put 12 volt battery here, I detached my gearbox. So what happened? I can get electrical energy here converted to mechanical energy. So I can have fan, I can have belt over here, I can even have like Tesla cars, I can drive a car or so and so. So I show you. So what I do here is exactly the opposite. So the mechanical energy is converted to electric energy. So it's easy to understand what do we mean by that. The only way we can do that is the Michael Faraday's laws of induction. And you can see, of course, this is a small version, and we have the two magnets over here, and then we have a coil. In fact, we can consider this coil, and then imagine the only way you can get electricity is by induction, which is Michael Faraday did that. So if I rotate this, well, of course, it's not connected to anything. If I rotate this, it depends on how fast it goes. I can get alternating current. So this is the way we do, but this one I'm getting direct current. So let me show you. So I had to connect this 12 volt, and then, well, of course, it's not going to be illuminated fully, because the reason why I said my output is only 6 volts DC. So let me try this so you can see. So this is another one. Let me just put this up so you can see. We can also use another electric motor, which is a smaller. Let me show you. See, this is a small electric motor. If I connect this, so I can use electrical energy to mechanical energy. So let me put this up. You can see. Looks like my gearbox came off. Okay, now it's okay. So if I rotate this, see what happened. See, you can see this fan. So the mechanical energy is converted to electrical energy, see? So this is easy to understand. What do we mean by conversions of energies? And let me put this down so we can start another one. Well, of course, I have a little bit more experiment, but I'll show you in a minute. And like I said a few minutes ago, I said energy means capacity to do work. And there are two main sources of energy. The most, or the ultimate, or the best for us is the sun, and also radioactive element. And then energy cannot be created, it's always converting from one to the other. And he was amazing scientist. His name was James Prescott Joule from England. And then he did this. Is measured in joules. Is the rate of doing work. So that's why we call it watt. And if you remember, he was amazing scientist in England, James Watt, and then he realized that the kinetic energy from the boiling water can, move the, kettle. Then that he was amazing scientist. I mean, he visualized, and then he became one with the horsepower and some other things, and the kinetic energy was born. And then they knew that, the water molecules are moving back and forth. They just so agitated, so that's why they make it. So that's why we call this 1 joule, which is the okay. And then we have two types. We have potential energy. We have the magnetic, we have gravitational force, we have chemical, we have electrical, we have elastic, and then nuclear. And the motion energy is heat, we have light, we have sound, and the kinetic energy. I have to explain a little bit about this energies. In United States, we have like almost, I would say, 90,000 dams. Because you know what, the rivers are supposed to be special. We have to have a gorge, we have to have a valley. I mean, you cannot put, generators on Mississippi River. It must be gorge, it must be valley, like, when we have in the Boulder Dam and some other places. Out of those 90,000, is only 2,300 dams are working. Well, of course, the others are also good. Sometimes they use it for the water reservoir, to supply for the houses. Sometimes they use for the flood control and some other things. But the hydro power happened to be the best. But unfortunately, we have used all of them. But the only option is left, I just researched a lot and a lot. I found out that the wind is the best. I mean, there is no other way we can do like a wind because it's a clean energy, it's sustainable. Well, of course, there is no doubt, the actual thing is, we have to invest a lot because like huge, like a 2 megawatt, 3 megawatt costs almost like $3 million. And imagine in 7 to 12 years it pays off by itself. But imagine that's so good. Well, once in a while they need like, maintenance and things like that. So these are the sources of energy. And like I said, hydroelectric and wind power, I will explain the wind power later. And the electron, and then we have the biomass, which is the wood and the waste crop. And no matter what, always we pollute the environment. It doesn't matter. The only thing we don't pollute the environment is the wind energy and then the hydroelectric energy. And then the nuclear energy and nuclear fission is also causing, the steams and the unfortunately, that is also expensive, nuclear energy, because, whenever we have like a hot water, the core is so hot, so we get the hot water, and the hot water is just transported to a special chambers, and then we get the steam, and no matter what the steam is like, those old days, steam engines, it's just turning the turbines, and like I said a few minutes ago, there is no other way. Always, in order to get electricity, you need relative motion, whether or not your coil is moving or your magnet is moving. And 99% of the time what we get alternating current. So the reason why we can transport it, we can just have transmission lines all that's 50 states everywhere. So that is so important that we do that. And then wind turbines, I will show you in a minute. And then the ocean power is a new idea. I have to explain this. Sometimes you are standing by the shore and then you can see some, where there's, small gulfs or, some like, would say, rocks. And then a wave is pounding back and forth, back and forth. So what happened when it's pounding against those boulders or huge, rocks, and coming back, it can generate electricity because water is going off, on, off, on, off. It's called the ocean energy. And then the other one is called geothermal. This is amazing idea. Unfortunately, we don't have this a lot. And what happened, I have to explain for the geothermal. Wherever the tectonic plates like this, they meet, or there's a crack in between, or there's a fault in between, this is where that happened. It's called geothermal. Geothermal energy is not bad, but of course, the bad thing is it's limited. And we have like in Iceland in two places, we have in New Zealand, and then we have in Japan, and there's one place in California which is not as big as those. But what happened, where those, boundaries are in the tectonic, and then the hot water comes in, and then the hot water is because it has a lot of kinetic energy converted to steam, and then after that, the steam can do that, can generate electricity. And then let me see, what else do we have? Wind turbine. And then wind turbines are so good. I have to show you in a minute. Let me, yes, I can do that over here. I had to make my own wind turbine. Well, of course, this is too small, but it works anyway. And you can see, this is called airfoil, and then birds were doing this for millions of years, but for the humans it's been 110, 120 years. And you can see this airfoil here, and you can see this part is flat and airfoil. So what happened, when the air blows here, this has to, rotate. But why? Let me explain this. I think I have demonstrated this for so many times. This is the wing from the, let me put this a little bit away. This is the wing from the airplane. And you can see this is airfoil also. So the wind is flowing much faster over here and the slower on the bottom. This was great scientist, his name was Daniel Bernoulli. And then what happened, the fast moving air here creates low energy, and then the high energy, pressure, low pressure and the high pressure, and the high pressure is moving this up. So that's why this airplane like 70, 80, 100 tons can go, lift. Helicopter is the same way, but this is the principle. And what happened, when the air is blowing over here, well, of course, these wings are amazing, 85 meters, and each one of them are 3-4 tons. So let me show you one. I think I can get my fan working here. I have a fan over here, so you can see when this fan is blowing, and then what happened, this aerodynamic of this blades causing it rotate. Well, of course, it doesn't show everything because there is a gearbox here and there's a generator behind it. Let me turn this on. You can see. So you can see how easy is the principle here, and let me explain a little bit here. So wind turbines are so good because you can have in the ocean, you can have everywhere. And like I said a few minutes ago, it doesn't matter, it's not like rivers that you have to have a special river, you have to have a special dam, and dam is also so expensive. But these are so good, And they calculated, the engineers and the scientists, that for 1.3 million for each megawatt, I'm talking about millions of watt. So if you have like 2 megawatt, it'll be 2.6. If you have like 3 megawatt, is almost like $4 million. And like I said, 7 to 12 years it pays off by itself. Well, of course, if you don't consider the maintenance and some other things. But this is the ultimate things for the humans to survive, because in United States we use this a lot. And then you can see in California, and when you go toward the Palm Springs, you can see there are so many places, because wind is always there. And then the amazing thing about this, you need like 7 to 11. The velocity of wind, 7 is not big deal. Sometimes the wind is blowing so bad, it's like amazing. You can have like 20, 30, but I show you in a minute. They have a brake, so they just break it so it won't get damaged. So this is the way the wind turbines work. I have a one. I have one over here. You can see. Let me put this down. So you can see, of course, this is not a complete, picture of everything. And then you can see the blades over here, and then the wind is blowing, and like I said, they're airfoil, and then they start rotating, and maximum they are like 10 to 20 RPM, and it's more than enough, because you don't need more because of inertia. And imagine 85 meters, it's a lot. It's not easy, because they use cranes, and it's so difficult to install those. It takes at least 2-3 weeks to install one, because that is so difficult. Then the main pole is so difficult, and this one, the pole, is not like the wings. It's like a concrete, huge concrete. So they put section by section, and some of them I think are 8 or 9. And then the old days they used to weld it. They realized it's not a good idea. Now they use the old system, which is like a pins goes inside, male and female, and that locks so good. So the poles are also so good. So here shows, this when these blades are rotating. So we got the 10 or 20 RPM, whatever that thing. But unfortunately, something is missing here. It's called planetary gears. Let me see if I can show you here. I removed this from the gearbox from the Ford. Let me see if you can see this. And this is called sun gear, and then we have the planetary gears, and they also goes in this. So what happened? This can multiply the rotation. So the planetary gears are here. So the first stage goes to like 74 RPM, and then the planetary gears, some of them, goes to 1,800 RPM, and then we have a generator over here, which is alternating current, and then it generates electricity, which 1,800 RPM is more than enough. Some of them are more, but it depends on. Overall, I have seen in Europe and so many places they do 1,800, and this is the way it works. And this is amazing, system, and it has also, you can see it's like a gearbox here. Then you have a smaller gear and bigger gear. So this can rotate 360 degrees, because wind is unpredictable. You never know it's, blowing this way, blowing that way, blowing vertical, horizontal. But on top of this gearbox, or this one which goes on top of the pole, there is like a velocity. It checks the velocity of air, and also the what way the wind is blowing. So that shows, and then this goes to electronic control, and the electronic control is just changing this yaw. So the yaw can turn like, 10 degrees, 20 degrees, 50 degrees, and it's amazing. Nowadays, everything is taken into the consideration. So they know exactly what they're doing, and then sometimes, once in a while, the gearbox goes bad. But you know what? I heard that, the normal life of this wind turbines are about between 7 to 12 years. Most of the time they last 10 years. It depends on how they build this. So this is the way they work. Well, of course, the old days I had to get this. This was like 3,000, 4,000 years ago. At that time, they had to use gravity. And imagine this is a bucket everywhere. So this was going in a river, so they could get, water to high elevation. The reason why at that time there was no pump or anything, this was used in Persia, this was used in Egypt and some other places, and this must be like at least 3,000, 4,000 years old. And sometimes I have seen that, they use cows or, horses, so it's going round and round, and then they're using this, scoop up the water, so it goes to the mother, place, and then goes for the watering the crops and some other things. Well, of course, this is a Hoover Dam. You don't see those things. I remember a few years ago I went there. This is a state of art is behind it, and they generate a lot of electricity, alternating current, and it's amazing how they do that. And the Hoover Dam is, I would say, state of art engineering. But how many times or how many places you can do this Hoover Dam, and imagine behind this dam there are billions of cubic meter water, and then if you go back in Ohm's law, you remember this is exactly like a voltage. So what it is, the voltage is there, the pressure is there, but you know what, we don't get any work. But as long as, as soon as we open those vents, and then, the water is flowing, the flow of water can do, work. So that's exactly, you have a battery sitting here, right? You don't see any motion or anything, but you have positive terminal and negative terminal. Well, when you put it on, like a fan or anything, and then current is flowing, so that's why you get the work. This is exactly what happened on dams. This is another picture. It is showing the Iceland geothermal plants. And then these are the solar cell, which unfortunately it is not that much, because in 1954 it was in Bell Lab, and the scientists realized that the silicon is a semiconductor. But I remember in electronic we read this like 4 or 5 years, and I know this for the fact that silicon is so good. But they came up with this clever idea. If you just dope that a little bit, well, doping means they add impurities. The reason why they want to get conduction a little bit more, because it's called semiconductor. So that's exactly what they do on these photocells, and then we can warm up your house and some other things. Well, of course, I have seen some in I think it was in close to Las Vegas. They have thousands of these, and then they're all connected together. But overall, it's a high maintenance. It's very difficult to do this. So this is another one, and then you can see here. Well, something important happened here when the current is in here. The voltage is generated here. It comes here. There is a huge transformer, and by the way, this pole is so huge because you can't use anything. You have to climb inside the pole, and then they have like a ladder. You can have everything. It's so good. Even this where the gearbox is so huge, people can stand. Well, of course it doesn't show here. So that transformer is a step up transformer. What it is, it is transferring to the voltage through the transmission lines. But you know what? This is a clever idea. If we don't step it up, so what happened? The voltage is thousands of volts, but the current is so low. Why they do that? Because they want to have less, loss. But if it's the opposite side, we lose a lot. So you can see those, pylons and huge pylons. It's a high voltage, and sometimes when you pay attention, you can see, the vibration, you can hear that. It's a high voltage, but it's a low current. So they transfer from Minnesota to California, California to Los Angeles, Los Angeles to New York City, and there's a minimum loss. So that transfer is doing that. Well, when that gets to your house, it's exactly the opposite. So you have the, a step down. So what it is, that high voltage is becoming, low voltage, which is 115 volts, but at the same time, it's just balancing each other. The current goes up, like in United States, is 7 amps, which is a lot. And this is like an ocean power I showed you a few minutes ago. And this is amazing. In 43 years ago, I was in Holland, so we made the tour like, I would say 2 weeks. That was a great moment in my life because this was pure science for me. I'll show you in a minute. I made my own windmill like this. Well, of course, it doesn't look good like this. And imagine those days, they had no idea about the, let me put this up a little bit more, you can see. They had no idea about the, there was no metals or anything. They had no idea about the airflow and everything else. But this is the way it works. See, anytime you have like a bevel gears like this, so you can convert vertical to horizontal, horizontal to vertical. So you can see it's called bevel gears. At that time, there was no metals or anything. But I had to take the whole day with this windmills, and then I realized they made their own. Let me show you here. So this was connected to those windmills, and this was connected to a huge, this part was connected to a huge slab, and there was a hole inside the slab, so they would put a grain, and there was another one underneath, so while that, this was rotating, the grain was going inside and getting, powder, so they would collect everything else. But in Holland was so different because this is the only country in the world that is below sea level. And nowhere in the world you cannot see this. It's 26.3% of the Holland is below, sea level. So what happened? That is causing a problem. But they came up with these fantastic ideas, and this one, I think the oldest one I saw was 500 years old. And what they did, that was amazing. They just did it with wood. Huge, poles, and they made their own gears. Well, of course, it wasn't as good as the one I showed you a few minutes ago. It wasn't as good as this, but it worked. See, it worked. It worked so good. So this was from the, huge, trunk of a tree, and then God knows how much time they did this, and then they just polished everything. And then once this was rotating, well, of course, it was, I would say the RPM was maybe 30 maximum. But those days, they didn't know about the airfoil, but you can see I graduated here like this. So you can see there was a small, woods like this, and because this was tilted a little bit, and no matter what, when the wind blowing, it doesn't matter. Either way, this will rotate, and then rotates the, it's called cranwheel and pinion, I call it, see, cranwheel and pinion, and then they would do the work. So, I mean, how amazing. I mean, imagine at those days they had no idea about the electricity or anything else, but that's the way they did. Few minutes ago, I talked about the radioactive element, and I have to explain this. What do we mean by radioactive element? Imagine inside the earth, and geothermal is one of those. Inside the earth, when after the Big Bang, what happened? Earth was still hot. It was like a molten thing. It takes 4.6 billion years. It still is hot, and then we cannot go like maybe maximum the Russians did like 12 kilometers, and there is no way. Some mines are like 3 miles below ground, and it's extremely hot because of that heat is coming. So beside the Big Bang, beside having that huge, I mean, molten thing in a core, we also have radioactive element, and uranium is one of them, 238. And uranium is amazing element. It has 92 protons, and this 238 is naturally in the earth. And what happened? I have to explain a little bit. Of course, this is a little bit complicated. For when we're talking about, nuclear physics. It's a spontaneous disintegration of atoms. This is called, nuclear decay. So what happened? They have a half-life and everything else. So inside the Earth we have the 238 uranium, and then we have 232 thorium and also potassium. So that decay is causing the heat, and that's why we have the geothermal things. But sometimes, I have to explain why some of them are so different. In some elements, we call it isotope. In other words, their chemical properties are exactly the same, exactly same neutrons on this one, but one of them has more. No, I'm sorry. Same protons, but some of them have more neutrons. So what happened? The chemical properties of this same element, but different mass, is exactly the same. But this one with the more neutrons has a little bit more mass, and you know what, it's not stable. That's why we're getting this heat from the earth. So we have thorium, we have potassium 40, and then uranium 238, and then iron has so many isotope, but the iron 56 is the more stable one. So 238 is stable. That's why we have this heat from the earth. And then the last part is for the global warming. I have to put this up. You can see this is extremely important concept in our life, because no matter what, we have this global warming. And then I have some examples over here. And to be honest with you, in this last maybe 40 years, I have seen a lot of climate change and also, well, of course, I know about the atmosphere, but not as good as they explain. But overall, my guess is the reason why we're polluting the environment beyond the repair, that's what happened. The ocean level is rising. The global warming is so bad, and then not only our atmosphere is getting so hot, everything else, also the ocean water is getting hot. So overall we have disturbed all things. The natural habitat for the animals is getting smaller. Polar bear is one of magnificent animal. But unfortunately, sometimes they get so hungry they have to eat their own cubs, because the water is getting so low. The ice is melting and so and so. But unfortunately, we don't take action, to stop this pollution, because, like I said, my investigation, my research shows that the only way we can survive is by the wind turbines. Well, of course, we also have the nuclear and some other things, but the wind is the best. So the global warming, and this is amazing. Carbon dioxide is one of them. Vapor, water vapor is another one, and the methane is another one. So what happened? Uh, these are causing the oceans and then everything else, the atmosphere and oceans to heat up. But you know what? I have some pictures over here. This is in France in 1933. You can see this glacier is almost like full of ice. But see, after 71 years, see what happened. This is the same glacier. It's almost, everything is gone. And then I will explain this later. And imagine, we could, colonize, Venus so easy because it's amazing planet. It's exactly like Earth. It's like the same, mass, same almost gravity, I would say. But the problem is huge. Is carbon dioxide. It's so thick. It's 92 times more than atmospheric pressure than Earth. Ours is 1.4. It's 92 times more. And imagine, it has huge, thick atmosphere like this, and then there's a sulfuric acid and carbon dioxide and everything else, and there is no way. Otherwise, we don't even have to bother to go to, planet Mars, which is no good. It has no atmosphere or anything else. But this one, gravity is good. The size is good and it's closer to us. But that's the problem, unfortunately. And this is the picture for the atmospheric think what happened for the pollution. And imagine sun's radiation, the electromagnetic waves are coming to Earth, and you can see here some of it is radiated back, some of them, not all of them, but some of them you can see this. You can see this magenta origin over here. That is a natural, but this part is not natural. You see how thick it is? This is the barrier. So in other words, this traps everything. So what happens? Some short wave from the sun comes in, and then they get trapped and they cannot radiate back. So what happened? They radiate back to the Earth, and that's what happened. And the global warming happened. And unfortunately, this is the only way we can stop the, CO2. Like, every time I see a Tesla in the street, I say, well, that's good. It's not polluting the environment. But, unfortunately, how many percent is Tesla? How many percent is, Mazda or, Toyota or the other cars? Fully 100% electric. Probably it takes another 100 years so we can do that. And unfortunately, this is the way it is, and then we have to, make sure that we do have this, and then the only thing we can survive. And the wind, I forgot something. Wind turbine can do for the United States 4.25 terabyte. It means that we are talking about billions of watt of energy. That's why they wind turbines are doing for the human beings. And then like I said, that is so important that we take this into the consideration. And I think that's all I could cover. Let me double check to see I covered everything I said. Yes, I did. And like I said, I'm hoping that you guys love my video, and then if you like it, you can subscribe. And anytime you have any concern or any questions, you can email me vahandavudyan@aol.com. I'll be happy to dig it out for you, even if I don't know the answer, and I'll let you guys know. Thanks a lot for watching, and I appreciate it.